Hello everyone, welcome back. Today we are going to be solving a question from the book Thomas Calculus, and this question is about infinite series. Sorry, I hope it's visible now. So it evolves around Helga von Koch's snowflake curve, and it's a way to make a snowflake basically. And this is from multivariable calculus, and we're discussing the topic infinite series. Also, this is my first video in my hostel, and that's why it took me a lot of time to upload a new video. But most probably I will be more consistent now, and also because I have a good maths paper coming at 7:15 p.m. So maybe if I get the question paper, I'll upload the solutions to that too. So let's start with this. So basically, this question says that we're constructing a snowflake using this thing, that we're taking some Cn, and that Cn starts with the first C1, which is just a simple equilateral triangle with, let's say, a side length A. Then you want to construct a C2 where you break each side of this first equilateral triangle into three parts. So you get A by 3, A by 3, A by 3, and you construct another equilateral triangle right here, and you remove this. Okay, so basically you're gonna get something like uh, this, right? So this star like thing. But as you keep increasing here, you would start to get something like this, and by the time you get to C4 you would literally see a snowflake coming. Okay, but Helga von Koch's snowflake is basically a snowflake which is found when you get to Cn with limit n tending infinity, right? And it looks like a perfect snowflake, I guess. I mean, I've never seen one more than C4, but I hope it does. So basically, the thing about Helga von Koch's snowflake is that the snowflake would be divided into so many sections that when we take the limit of n tending infinity of the nth perimeter, let's say Pn, we would have this tending to infinity. But the area of this figure would still remain finite. So we would be able to compute the limit n tending infinity of an, the nth C area, right? So that is basically what the question is about. So it's given that it's a curve of infinite length that encloses a region of finite area. So this is the curve, and we need to first find the length ln of any nth curve, and we need to show that this ln, this thing, we need to show this, the perimeter of nth C. Okay, so let's start with the answer. So first thing that we can do is that we will get perimeter perimeter of n, let's say Pn. It would be basically, I'm just making a few random variables. So my first random variable is that I have some ln. Okay, ln is the length of nth C, side length of nth C. So side length means that any, like, even if it's something like C2, I would have, I would count this as a side length, right? I would, yes. So all these A by 3s would be my side lengths. So if I notice correctly, I would see that the ln, if I see the ln, it would be A divided by 3 power n minus 1. And for mn is the number of sides. So as we keep progressing to different c's, we will see that the number of sides is also increasing, and therefore the number of sides If we check once, we'll get that it is 3 times 4 power n minus 1. Okay, so basically these are the things that we are gonna solve our question around. Okay, so the nth perimeter would just be the length of a side multiplied by the number of sides. Okay, so this would be a divided by 3 power n minus 1 times 3 4 n minus 1. Okay, so this is 3a times 4 by 3 power n minus 1, and clearly we can prove that as limit n tending infinity, Pn is just limit n tending infinity 3a 4 by 3 power n minus 1, and as 4 by 3 modulus is greater than 1, this thing diverges, right? Won't be able to find the limit, and this limit does not exist. So we are able to prove that the perimeter would go to infinity as we increase the value of n. Now let's talk about the area, which is the main part of our question, right? So we've done the first part. We've written ln as a function of n as well. This is the function of n. And now we're asked about the b part. Find the area an of the region enclosed by Cn and show that this thing. Okay, so first let's write an as a function of n, right? So for an, so the main part of the question starts with an. Okay, so for the first one, if I check, I would have a1 would be root 3 by 4 a square, and a is basically the length of the first one, right? So I was using this variable called ln. I'll use it here because I want to simplify my problem. So root 3 by 4 times l1 square, this is my area 1, right? So uh, when I go down, I see that when I'm getting the second area, so basically this was my first C1, then I added these three things, right? So first I need to get area 1 plus, now I'm adding three things. So first I'll multiply it by the number of sides. So number of side is mn, and mn is 1. So m1, I've multiplied by m1. M1 times root 3 by 4 a square. Now what is the a is a by 3 now, so it is l1 divided by 3 square. This is basically root 3 by 4 a square, but the a is now a by 3. That's why I've used L1 by 3. Okay, so if I check for A3, it would be A2 plus M2 times root 3 by 4 L2 by 3 square. Similarly, right? Because in A3 also I would have this A2, and then I will add these more, right? That's the only difference. So I have done this correctly for A3 as well. And if I go to AN, I would get that it is equal to AN minus 1 plus M n minus 1 times root 3 by 4 L n minus 1 by 3 squared. Right? Now, if I put in the value of m n minus 1 and l n minus 1, right, because I have these ln and mn as functions of n, so if I use that, I would get an is equal to an minus 1 plus this whole thing 3 by 4 cube times 4 by 9 power n times root 3 a square. I've already calculated it so that you don't find a problem in it. And because this is such a big term, I'm just letting uh, there exists a case such that k is equal to 3 by 4 cube times root 3 a square. Okay, so this is my some k value. So I got a2 minus a1 is equal to k times, okay, sorry about that. A2 minus a1 would be k times 4 by 9 square, and similarly I would get a3 minus a2 to be k times 4 by 9 cube. And if I just go down, I will find that I have constructed a recursive relation, and if I add all these equations, I would cancel everything and I would be left with an minus a1, which is equal to this simple geometric series, right? And I can just use this, and I don't even need to because uh, finding a nth a if I want to find the function of nth area, that would be a long process, and I think that's pretty obvious by now how to find. So I won't do that. I would just clearly jump to limit n tending infinity an, which would be the infinite perimeter area. It would be a1 plus k times this whole thing, 4 by 9 square divided by 4, and this. So I would, if I just put this as root 3 by 4 a square and compute the values of this, I would be left with root 3 by 4 a square times 1 plus 27 by 45, and this would just compute to be root 3 by 4 a square times 8 by 5, which is just 8 by 5 a1. This is an as limit n tends to infinity. So that's what I had to prove, and we have done it. So basically this is what we call the Helga von Koch's snowflake curve, and I have correctly proved that the perimeter of this thing, as n tends to infinity, we create an infinite number of sides. It would tend to infinity as well, but the area would remain finite as we increase the number of n. And I hope it's clear. uh, I hope it wasn't a very long explanation, and I hope you enjoyed it. This was my first video from my hostel, and I hope I can make the same quality of content. Thanks for watching.